Hello everybody, we're getting ready to do lesson 5.5, part 1 of Pre-Calculus Math today. Email me here for course material, solution PowerPoints, class worksheets, homework sheets, etc. And today, 5.5 multiple angle and product to sum formulas, part 1. You have 6 points here on your notebook, into your notebook, or if you have your notebook guide. And then 58 points here on your classwork. Today's bell work, teachers and students. You have an issue here, find a radian measure of the central angle of this. Then down here, find the length of the arc. So find an arc and the radian measure of central angles. Give your students 5 to 6 minutes, teachers. Okay, welcome back for your solutions of today's bell work. For 139, S equals R theta, which goes to theta, in this case here, equals S over R. We know our S over R, and we're trying to find theta, which is our radian measure. 7 over 15 equals 0.467 radians. And then down here, find the length of the arc on a circle. So S equals R theta equals 21 times 35 degrees times our conversion factor here, pi over 180. When we crank that through, we get 12.828 centimeters for 140. Okay, into our first notebook slide for 5.5 part 1, multiple angle formulas. In this section, you will study 4 additional categories of trigonometric identities. 1, the first category involves functions of multiple angles, such as sine Ku and cosine Ku. 2, the second category involves squares of trigonometric functions such as sine squared u. 3, the third category involves functions of half angles such as sine u over 2. So this is our third category here. This goes in your notebook, students, so either have your notebook guide or take this down. Page 2 goes into your notebook. You should learn the double angle formulas below because they are used often in trigonometry and calculus. So double angle formulas, this should definitely go into your notebook and into your memory actually. Sine 2u equals 2 sine u cosine u. Then tan 2u equals 2 tan u over 1 minus tan squared u. And then cosine 2u equals cosine squared u minus sine squared u. And then this yields this, 2 cosine squared u minus 1, which is what this is equal to. And then this yields this down here. And then we can further simplify this to 1 minus 2 sine squared u is what this yields here. So these are your double angle formulas. Write these down and memorize them. On to our next example here, solving a multiple angle equation. So solving 2 cosine x plus sine 2x equals 0. So begin by rewriting the equation so that it involves functions of x rather than 2x. So we need to get rid of this here, this 2x, so that it's just x. Then factor and solve as usual. So 2 cosine x plus sine 2x equals 0. That's your original. And then your double angle formula. Using one of your double angle formulas, 2 cosine x plus 2 sine x cosine x. That's what this becomes here. It yields this double angle formula. And then we can factor out 2 cosine x equals 1 plus sine x equals 0. That's after our factoring. So we have 2 cosine x equals 0, and we have 1 plus sine x equals 0. So for that, this will become cosine x equals 0, and then sine x equals negative 1. So are both those solutions? Well, they will, within the interval of 0 to pi, this will give you pi over 2, 3 pi over 2, and then this will give you 3 pi over 2 will be your solutions. You can check it with your graphing calculator. Let's try one now using a graphing calculator to approximate the solutions of the equation between 0 to pi. If possible, find the exact solutions algebraically. So sine 2x minus sine x equals 0. So we don't want to deal with that. So here's our solutions here. Thank you very much. So we just jump to that. But how do we get there? So we have sine 2x minus sine x equals 0. And then we have sine x equals 0. So when we solve for that, and then we have 2 cosine x minus 1. This is one way that you can pick this apart and solve each one of these individually like that. So we have 2 sine x cosine x minus sine x equals 0. So this will yield this here. And then when we factor out a sine x, we end up with 2 cosine x minus 1 equals 0, and sine x equals 0. So 2 cosine x minus 1 equals 0. We still have to solve that for this part of our expression here. But sine x equals 0 will give us 0 pi, and then x equals 0 pi over 3 pi and 5 pi over 3, which are these solutions here. They correspond to when x equals 0 down here. And then over here for 2 cosine x minus 1, we have this will give us cosine x equals 1 over 2, and then x will be pi over 3 and 5 pi over 3, which corresponds with this and corresponds with that. So it doesn't respond to that, but 3.142, that's your pi, and then this is your pi over 2. Let's see, pi over 2. No, that's pi over 3. I don't see pi over 2. There is no pi over 2, but there is pi over 3, and then 5 pi over 3 is here. So these are your solutions here for this expression here. So that's kind of like the idea, is you break this down by using your formulas that we looked at. Okay, let's go into another example here. Evaluating functions involving double angles. Use the following to find sine 2 theta, cosine 2 theta, and tan 2 theta. So cosine theta equals 5 over 13, and then between, in this interval here, 3 pi over 2, less than theta, less than 2 pi. So within that interval, which is this angle here, that corresponds to this angle here, 3 pi over 2 is down here, then this is 2 pi. So this is 5 and negative 12. So, okay, then this is 13 here. So our hypotenuse is 13. 5 over 13 would give us our cosine on this. And this is our theta here. Okay. In the figure, you can see that sine theta equals y over r. Here's our y, or 5 here. See, y over r is 13, so our y is right here. Negative 12 is our y, and then 13 is our hypotenuse here. And tan theta would be negative 12 over 5. So then this segment here of our triangle will be 5. So tan theta would be the negative of 12 over 5. Knowing that, consequently, each of the double angle formulas, you can write the double angles as follows. So sine 2 theta equals 2 sine theta cosine theta, which will give us equals 2 times sine theta is negative 12 over 13, and then cosine theta would be 5 over 13. And then that'll give us a negative of 120 over 169 as a double angle for that one. Find cosine 2 theta. So cosine 2 theta equals 2 cosine squared theta minus 1 when we transform that into this here. So 2 times cosine squared theta will be 25 over 169 minus 1, would give us a negative of 119 over 169. So there is our solution to that. And then find tan 2 theta, and then this is our equivalent expression for tan 2 theta. Will be 2 tan theta over 1 minus tan squared theta. And then we plug in our values here for this. Since we know that 1 minus tan squared theta will be 1 minus tan squared will be negative 12 over 5. And then 2 tan theta will be negative 12 over 5. When we crank that out, we get 120 over 119. So that's how we would find this with this angle here. Okay, let's try one now. In these exercises, find the exact values of sine 2u, cosine 2u, and tan 2u using the double angle formulas here. So we have sine u equals 3 over 5, 0 less than u less than pi over 2. So within these conditions here, for cosine u, let's go with cosine u here. We get 4 over 5 by using this triangle here, these triangle measurements here. If our sine u is 3 over 5, so this is our u here, sine, this would be 3, this would be 4, and this would be 5 here. So sine 2u will be 2 sine u cosine u. This is our equivalent expression here using a double angle formula. So it'll be 2 times 3 over 5 times 4 over 5 will give us 24 25ths. Here's our 5, here's our 3, and here's our 4. So cosine 2u, knowing what our sine 2u is, will be the same thing as cosine squared u minus sine squared u, equals 16 25ths minus 9 25ths. Okay, here's our squares here for that. Cosine u, remember up here, be 3/5, and then our 4/5 would be here. Cosine u and sine u. And then once we combine these two values, we get 7 over 25. And then tan 2u would be 2 tan u over 1 minus tan squared u. We plug our values in now. We get 2 times 3 over 4 over 1 minus 9 over 16. And that'll yield us 24 over 7 for tan 2u for this triangle here. In your notebook, double angle formulas are not restricted to the angles 2 theta and theta. Other double combinations such as 4 theta, 2 theta, 6 theta, and 3 theta are also valid. Here are two examples. Sine 4 theta equals 2 sine 2 theta cosine 2 theta, and cosine 6 theta would equal cosine squared 3 theta minus sine squared 3 theta. By using double angle formulas together with the sum formulas derived in the preceding section, you can form other multiple angle formulas. Example 3, deriving a triple angle formula. So to rewrite sine 3x in terms of sine 3x, or rather, rewrite sine 3x in terms of sine x. So to reduce it down to just sine x, sine 3x equals sine 2x plus x. Rewrite as a sum. So we can rewrite this thing. We can turn this into this down here. And then once we have that, once we can use a sum formula, sine 2x cosine x plus cosine 2x sine x. So this is our sum formula where we can plug into that. And then this will turn around and equal 2 sine x cosine x plus 1 minus 2 sine squared x times sine x. Here is our double angle formula that we plug in to here, because these are double angles. And then when we multiply out, we get 2 sine x cosine squared x, 2 sine x cosine squared, this is a cosine squared x, plus sine x minus 2 sine cubed x. So now we have a cube in there. So Pythagorean identity. 2 sine x, and then we have 1 minus sine squared x plus sine x minus 2 sine cubed x. So we can separate this out, 2 sine x. This is part of our Pythagorean identity here. This becomes 1 minus sine squared x. And then 2 sine x minus 2 sine cubed x plus sine x minus sine cubed x. We're going to multiply through again. And then we're going to simplify out now. 3 sine x, so 2 sine x, and then we have a sine x here. That'll be 3 in sine x. And then negative 2 sine cubed x and negative 2 sine cubed x is 4 sine cubed x. We can simplify that. So we can simplify it that far. We can go into a triple angle. So use double angle formula to rewrite the expression. Use a graphing calculator to graph the expressions to verify that both forms are the same. So we have 8 sine x cosine x, and then down here we have 4 sine x cosine x plus 1. So if we factor out a 4 here, we get 4 times 2 sine x cosine x, which is the same thing as 4 sine 2x here, 4 sine 2x. Let's see, 4 sine 2x. This, because it is a double angle, it'll factor down into sine 2x here, sine x cosine x. Will factor back into sine x, this here. So we have 4 sine 2x with that one. Graph this and graph that, and they should be the same as this. They should all be the same. And then down here, 4 sine x cosine x plus 1 will become 2 sine 2x plus 1. When we factor out a 2 here, 2x plus 1, let's see, 2 sine 2x plus 1, using our double angle formulas again for this one here. Power reducing formulas. The double angle formulas can be used to obtain the following power reducing formulas. So again, I've included this in your class worksheet. Because I think it is very important. So it should be in your classwork sheet, students. Sine squared u equals 1 minus cosine 2u over 2. And then cosine squared u equals 1 plus cosine 2u over 2. And then tan squared u equals 1 minus cosine 2u over 1 plus cosine 2u. So these are important when you hand those in today in your classroom. I should get them back to you the next day. If not, you can go back on YouTube and put this in your notes, but I want to make sure that you get this down. So that's why it's included on your classwork sheet. Okay, let's go and try another example here. Example 4, reducing a power. Rewrite sine to the 4th x as the sum of first powers of the cosines of multiple angles. So sine to the 4th x equals be the same thing as sine squared x squared, property of exponents. And then we can reduce this back using our 1 minus cosine 2x squared over 2, using our power reducing formula. And then again we can factor out a 1/4 here. And then when we square this out, well, it'll be over 4. Then we can factor out that 4 so we don't have a fraction here. But in your numerator, you'll have 1 minus 2 cosine 2x plus cosine squared 2x. So we expanded this binomial into this. And then when we distribute our multiplication through it, we'll get this expression here. And then when we combine like terms, we get 3/8 minus 1/2 cosine 2x plus 1/8 cosine 4x. And then when we can factor now, we can factor out a 1/8. And we get 3 minus 4 cosine 2x plus cosine 4x. And then we can check it to check the result here, y1 sine to the 4th x. And then we graph y2 as well. You can see that it does graph right along with sine to the 4th x. Check your table values too as well, and it should show up there. Let's try one now. cosine to the fourth x. Let's factor that down. This is on your class worksheet. So this will be cosine x when we factor this back into two binomials here. Or it's a perfect square is what it is. Cosine to the fourth x is cosine squared x, cosine squared x. And then we can use our reducing formulas here to 1 plus a cosine 2x over 2 and 1 plus cosine 2x over 2. And then this will become here when you multiply these two together. You get this up here over 4. And further reduction here will give this over here, and then this part of the expression will be 1 plus cosine 4x over 2 by using the power reducing formulas for that. And that's what we end up with there. And then you can graph to check it. This should be the same as that on your graphing calculator. And we're not done yet. So we're going to reduce it back because we got rid of our 2 over here. We got rid of that fraction, so now this is over 8. And we combine like terms up here, and then we factor out 1 over 8. And again, this should be what's the original expression when you graph these two. That will equal your original expression on your graphing calculator, as well as your table values. And that is 5.5 Part 1, Pre-Calculus Math. Email me there for course materials, solution PowerPoints for homework, and other note-taking guides. Thank you.